Hello and welcome to Meta-Evidence Articles, where we encourage community research and education with weekly articles. I'm your host, Benton Loeyball, and this week we are talking about new strategies to tackle high cholesterol. Are robots more dangerous than cholesterol? No. When I think of the most dangerous things in modern society, the things most likely to kill me, robots are pretty much at the top of the list. When I examine the statistics, however, OSHA reports only about 2 deaths a year from robots. The leading cause of death in the US, on the other hand, is the same as it has been since 1921, heart disease. A significant cause of this burden is high cholesterol. While cholesterol-targeting medications like statins have led to a major advance, there are still far too many people suffering from cholesterol-exacerbated heart disease. New technologies, not robots, are using nucleic acids such as RNA and DNA to boost our body's ability to get rid of dangerous proteins and molecules. Unlike robots, each of us is unique, as shown in our DNA, the code that defines what we are. DNA on its own doesn't really do much. Proteins are the machines in our bodies that get things done. To make proteins, the body first transcribes DNA into messenger RNA, or mRNA. The mRNA then carries the instructions to cell structures that build proteins. This is essential to translate the genetic code, or nucleic acids, the NA in DNA and RNA, into amino acids, the building blocks of proteins. The amino acids are assembled and folded into the final protein, which, in the case of high cholesterol, can cause problems. Nucleic acid-based approaches lower cholesterol by interfering with the body's ability to turn specific pieces of DNA into functional proteins that would normally increase cholesterol in the blood. There are many proteins that contribute to dangerous cholesterol levels. Before we jump into those, a quick refresher on cholesterol. Cholesterol is a necessary component of all cells, but excess cholesterol that our body doesn't need travels in the bloodstream where it can accumulate and cause damage. Particularly dangerous carriers of cholesterol include triglyceride-rich chylomicrons, LDL or low-density lipoprotein, and lipoprotein(a), also called Lp(a). Luckily, new technology, still not robots, and epidemiological data have identified several specific genes and proteins that are associated with higher cholesterol levels. Some of these, such as Lp(a), have been previously impossible to target. A few of the key proteins follow. APOC3, or apolipoprotein C3. Free triglycerides in the blood are frequently carried by large chylomicrons, which are broken down into remnants and packaged into safe forms or destroyed by the liver. APOC3 binds to the chylomicrons and prevents them from being cleared effectively. Medications that target APOC3 show promise for people with high triglycerides without other cholesterol markers. PCSK9. Proprotein convertase subtilisin kexin type 9. The liver absorbs LDL through special proteins on the surface of liver cells called LDL receptors. These bind to LDL particles, pull them into the liver cells to be destroyed, then move back to the surface to gather more. PCSK9 can also bind to LDL receptors. This has a double whammy effect. It keeps the receptor from binding and recycling LDL particles, and causes the receptor itself to be destroyed. Lowering PCSK9 would allow the body to remove LDL particles at a higher rate. APOA or Lp(a). APOA binds the cholesterol to form Lp(a), a special LDL-like particle that has all the bad effects of LDL on overdrive. Lp(a) carries cholesterols in the bloodstream and deposits them, causing plaques and inflammation. More than 1 in 4 adults with atherosclerotic cardiovascular disease, or ASCVD, have Lp(a) levels above the danger threshold. Even worse, Lpa levels are determined by genetics, and medicines like statins do not affect this dangerous particle. Nucleic acid targeting medicines are effective at lowering levels of proteins by a few different methods of interfering with gene expression. Each method works by targeting RNA or DNA to reduce or silence the production of specific proteins associated with disease. Antisense oligonucleotides, or ASOs, are short, single-stranded bits of synthetic RNA or DNA. These bind with molecules inside a cell's nucleus and destroy mRNA that's on its way to be turned into a protein. It's like cutting the cable between a laptop and a printer. The end result is that the RNA doesn't make it to production, and the final protein, in this case APOC3, PCSK9, or APOA, doesn't get built. There are many medications which use antisense oligonucleotides, including those that target APOC3. Volanesorsen has undergone many clinical trials, including the COMPASS and BROADEN trials, which have found significant 71 to 88% reductions in triglycerides after 3 months. Olezarsen, which has recently shown top-line results from the CORE and CORE2 trials, showing 49 to 72% reductions in triglycerides after 6 months. And APOA, or Lp(a). Pelacarsen is an antisense oligonucleotide medication in Phase 3 Horizon clinical trials, which targets APOA to reduce Lp(a) levels by up to 80%, depending on dose and frequency. Small interfering RNA, or siRNA, is a technology that mimics the body's natural regulatory mechanisms. The body uses them to selectively reduce the amounts of specific genes and to defend against viruses. siRNAs are different from antisense oligonucleotides because they recruit a special machine, not a robot, in the cell nucleus that hangs around and lowers levels of the target gene or protein for a prolonged period of time. Medications that use siRNA to limit cholesterol target PCSK9, like inclisiran, which was the first FDA-approved siRNA cholesterol medication in 2021. The Orion studies showed a 50% drop in LDL levels after 18 months, and Victorian trials are ongoing for additional uses. They also target APOA, or Lp(a). Olpasiran is currently undergoing Phase 3 trials, and earlier trials showed Lp(a) reductions of up to 90% after 3 to 6 months. These ongoing clinical trials need people to make them happen. Robots simply won't cut it. Heart disease may be the most likely cause of death in America, but with the help of clinical trial investigators, staff, and participants, it may become less dangerous than robots. Especially if the robots decide to have a robot uprising and kill us all. Thanks for joining us on this week's episode of MedEvidence Articles. If you'd like to know more, all of our descriptions are linked in the podcast description below. You can also visit our website at medevidence.com. MedEvidence helps answer the question of who can you trust for medical information. The MedEvidence platform provides valuable information about many medical issues and the insights of evidence-based medicine. MedEvidence educates audiences through engaging and entertaining magazines, podcasts, videos, articles, and presentations. We strive to bring together diverse voices of top-level medical professionals, researchers, and experts to provide unique and engaging content that uncovers the truth behind the data. For more great content, including discussions by physicians and subject matter experts, check out the MedEvidence podcast. My name is Benton, and we'll see you next week.